Right. Shall we get started with the final talk from the last session? Okay, before we get started, a little announcement from Basis. So Basis has t-shirts there that anyone can take. And we will put up a link to RSVP for dinner if you haven't already, so we know how many people to expect. Okay, so I think we'll play the recording now of the last talk, and then we'll start a poster session afterwards.
Hi, everyone. Thanks for coming to my talk. I'm Jacob Laurel. I'm a PhD student at UIUC, and I'm here to tell you about abstract interpretation for automatic differentiation. And first off, I just want to thank my collaborators who are listed here. Without them, this work would not be possible. By the end of this talk, I will hopefully have convinced you why automatic differentiation needs precise, general, and scalable static analyses, and why this is actually an obtainable goal. Automatic differentiation is everywhere, whether it's graphics, scientific computing, and of course machine learning. It pervades computer science. Now, what actually is automatic differentiation? Well, imagine I have this function, the sine function, which is differentiable, and I've implemented it as a program. Well, since it's a differentiable function, I can think about having another program that computes that derivative. Now, turns out this program can be constructed automatically using the rules of calculus. In fact, it's exactly what things like PyTorch, JAX, and Enzyme all do for you fully automatically. Now, as mentioned, we're going to be interested in analyzing that derivative computation. So, to motivate why, let's start with the story. Once upon a time, this was me in my apartment. I was trying to program this Arduino in order to get fixed point arithmetic Bayesian inference to run. So I got this fixed point arithmetic library, I compiled everything, and then when I tried to run it, I got an assertion failure. The program crashed. Now, after a bit of debugging, it turned out that the culprit was because a derivative had overflowed past the fixed point number's allowable range. So we can actually generalize this issue into the following problem statement. Find all possible derivative values that a program might encounter. Now, of course, that's useful to check whether or not derivatives overflow, but also this formulation can be used to test whether or not a function, like a neural network, is monotonic. This formulation also allows us to ask the question about how sensitive a function is to different inputs. Now, these derivatives that we're going to analyze are computed with automatic differentiation, and we're going to analyze them with abstract interpretation. And thus, these two form the combination that underlies my work. Now, it's not easy because there's a challenge that we have to contend with. Specifically, we want the analysis to be precise, general, and scalable. This is not easy because in automatic differentiation, we have to contend with things like higher derivatives, nonlinear functions, non-differentiability, etc. So, as a first step in this direction, I'm going to present a little bit of our past work that was published in OOPSLA last year, whereby we find ways to synthesize precise static analyzers for automatic differentiation. Here's the programming language a developer would start with. They would program some differentiable function in this language. So their original program might look something like this. And here we can see it has the sigmoid. Now, the derivative computation will actually look like this, whereby we have to compute the derivative of that sigmoid using the chain rule. Now, if we were to try to abstractly interpret this computation, we would have to normally abstractly interpret each primitive operation, like the sigmoid, the multiplication, etc. Now, the problem is that loses precision. So our strategy is Passato, and Passato is able to come up with an abstraction for the entire group of nonlinear operations. To see why, let's look at the graph. So on the right, we have graphed the mathematical expression that corresponds to this group of nonlinear operations. Now, even though it's nonlinear, it's very close to being linear. In fact, we can actually use a linear approximation of this nonlinear pattern. Now, we then have to enclose that linear approximation in order to obtain soundness guarantees. And of course, the most important part of these guarantees involves computing this term D, which governs the soundness enclosure. It's not super easy because we immediately notice that solving for that D is a non-convex nonlinear optimization problem. And not just for the chain rule, but also for the product rule and the quotient rules of calculus as well. But it turns out that in the paper, we prove that there are efficient solutions to this optimization problem. Now, you may be wondering how well this works in practice. Well, let's see an example. So here we have a climate model governed as this ordinary differential equation. Now, the program that we're interested in analyzing is actually the numerical solver for that differential equation. And we're going to automatically differentiate through that program, which is just a solver. And this will allow us to perform a sensitivity analysis using automatic differentiation. Now, we want to perform this analysis for a range of conditions, and this is why we need abstract interpretation as well. So here we can see the results, noting that the blue dots correspond to just regular evaluations of automatic differentiation, and thus the goal of abstract interpretation should be to, as tightly as possible, enclose those blue sampled points. In fact, we actually do see this, that Pisato's bounds, shown in purple, are indeed the most precise, compared to an interval or zonotope abstract interpretation. We also have some ongoing work in this direction focused on graphics, whereby coordinate neural networks are an architecture that is used to essentially memorize an image or scene. Now, the local Lipschitz constant of these networks influences their expressive power, and so to get bounds on the Lipschitz constants, we use our technique Pisato. Indeed, Pisato is able to get orders of magnitude more precise bounds. So again, we revisit the space of challenges. And in the next work I'm going to discuss how we were able to solve the non-differentiability challenge. So recall our programming language that the developer will write a differentiable program in. Now, if we add a branch primitive to the language, we run into some issues, namely that this now allows for the potential to encode non-differentiable functions, like this ReLU function being non-differentiable at the origin. As a solution, we propose DeepJ, which is the first abstract interpretation of Clark generalized Jacobians. Clark generalized Jacobians allow us to handle both differentiable and Lipschitz, but not necessarily differentiable functions. And so we can define an abstract domain to over-approximate Clark Jacobians. And of course, in the paper, we prove the soundness. So it might help to see an example. So here we have the following. We have a neural network, but we also have a perturbation that acts on the input to that neural network. Now, this perturbation involves these min and these max functions, and thus there is some element of non-differentiability in the perturbation. But our work is able to get derivatives of the neural network with respect to the perturbation amount, something that no prior work was able to do. And thus we can actually certify Lipschitz robustness with respect to the perturbation. And indeed, we can even scale this up to not just simple neural networks, but actually large convolutional networks as well. So we revisit these challenges, and the last one that I'm going to describe is how to support higher order automatic differentiation. Now, higher derivatives are used in a variety of places. In particular, we were interested in cases like in explainable machine learning, where you have to explain the interaction between multiple features. Now, the question then becomes, how do we get tight certified bounds on these higher order derivatives? Well, it's not super easy because here's the challenges. First off, there's way too many nonlinear patterns to try to customize an abstraction for each one. That would be incredibly cumbersome for the abstraction designer. It would also be very tedious to try to reprove soundness for each order of derivative or each abstract domain one wishes to use. And furthermore, there's a strong dependency across higher order derivatives, the exponential function being a great example. Our solution is to co-design a concrete and abstract automatic differentiation metasemantics. Now, this will allow us to reduce autodiff reasoning to just reasoning about standard programs, and it will be designed in a way to capture as much dependence information as possible. So to conclude, now when I go back to my desk to try to program an Arduino to run differentiable inference, instead of getting an overflow, you get a paper, because we solved the overflow problem using the techniques that I just described. And that's because static analysis of automatic differentiation is now precise, general, and scalable due to the techniques I developed. That being said, though, there's a lot of exciting future directions that we can apply these to, so stay tuned. Thank you.